straight, and I'll do the other one simple. All right. Let's see. All right, so derivative rule. Rule 1. What's the derivative of a constant? Now that one's an easy, simple proof in your book. You can look at it. It takes about 3 seconds and you're good to go. Okay? But just use common sense. What's your, if you have y equals f of x equals 3, what's that graph look like? Or we say a straight line, or all, you know, in Euclidean, all lines are straight, but horizontal. Okay. Now, isn't that a line? So the derivative is the slope of that line. So if it's horizontal, what's its slope? Okay. Now they do a simple little proof. It's simple, easy to follow. Now, what you cannot do is get limit confused with derivative. They are not the same thing. All right, do you understand that limits are y values that you're getting close to? And then when you say, what's the limit of this function as x approaches 4, you're saying on that graph, when x is getting close to 4, what's y getting close to? Is everybody with me? But derivatives, one of the easiest way for me to remember, it's not the only thing they are, but one giant application is they are slopes of tangent lines. That's not the same thing as the y value on a curve. So the reason I'm emphasizing that is people get these two things confused all the time. What's the limit of a constant? The constant. What's the derivative of a constant? 0. See, if I'm on this graph, y equals 3, no matter where you are on the graph, what's your y value? 3. That's why the limit of a constant 3 is the constant 3. But the derivative, because it's the horizontal line, the slope of that horizontal line is what? 0. And your brain will flip on you if you're not careful on a test. So the limit of a constant is the constant, but the derivative of the constant is 0. Okay. Let's do the power rule. All right. If I've got a single variable to a numerical power, then my derivative looks like this. Now, they do a really nice proof of this one in the book. I'm just going to hand wave at it for a second because I don't have time to do the whole thing. All right. They kind of show you if you start doing your definition. Now they use delta x's instead of h's. Everybody with me? That's the only thing that they're doing different. All right. The key is when you've got this f of x plus h. Over here, your f of x is x to the n. Is everybody with me? So I've got x to the n right there. That's my f of x. So this is going to be x plus h to the what? I mean, does everybody understand that your f of x here is a constant and your f of x on this one is like x to the n, like x to the 5th or x to the whatever, okay? So this one's not a problem. This one, you have to kind of know how to do a binomial expansion. So they kind of do one, they kind of start it for you. I'm not going to keep going. But do you understand that if you have like x plus 8 to the 5th, eventually you're going to have an x to the 5th? And at the end, you're going to have an 8 to the what? 5th. And then you have a bunch of stuff in between. Okay? The binomial expansion, they kind of shows a bunch of stuff in between. The first one is an x to the n. And then this second one is your nx to the n minus 1 times your h. And then it starts getting more complicated. Okay, so you can go look up that binomial expansion if you didn't have it in high school. I mean, they kind of show it to you for your next coefficient. You got like n times n minus 1 over 2 times x to the n minus 2 times h to the second. It just keeps going, and then finally your last one ends up being h to the n. All right. Now, what ends up happening is the first and the last one go out, and all the rest of them have a button on it. All that's over h. And then you got that minus x to the n, your f of x, and all that's over h. So do you understand that this x to the n and that x to the n will end up going out? Now, do you see that everything has h's in it now? What's the only one that has one h? This one. So when I factor the h out, does everybody understand this will be the only man standing? All the rest of them are going to have h. When I factor out an h, I'm going to have an h left. When I factor out an h on the next one, I'll have a bunch of h's. Everybody with me? So what's going to happen when all those go to 0 later? So what's going to do to every term after this one? It's going to do what? It's going to wipe them out. So that's why this ends up being your derivative rule. Now, so do we understand if you had something like this? So my example would be if you had y equals x to the 5th, and they want the derivative. Remember that little prime's your derivative symbol. Notice where this n comes. This n comes down and becomes your coefficient. So that means that 5 comes down and becomes my coefficient. My variable stays the same. Now later, those are going to be more than variables. They're going to be entire expressions. So we might as well start now. That numerical exponent comes down and becomes the coefficient. Your expression, which is just x here, stays the same. And then what happens to your power? Up or down? Down by how many? So what's my power going to be here? Okay, so your power comes down. Okay, now sometimes it's a bit hidden. Now, what do I mean by a bit hidden? What if instead I gave you this? Y is the square root of x. That's right. Now I can change it to a power and use my power rule. All right, that's x to the 1/2. So what's my derivative going to be? What am I going to do with that power? Hold it down, it's my coefficient. My expression stays the same and my power goes down by 1. So what's 1/2 minus 1? A negative 1/2. Now, they do not like negative exponents in the back. So if you go to the back, it's going to look like this. They're going to pull that to the bottom, make it a positive what? 1/2. And then because they gave it to you in a root, they're probably going to put it back in a root. So you turn to the back, they're going to have 1 over 2 times the square root of what? I don't, but when I'm plugging numbers in, especially if I don't have a calculator, it'd be better for me to plug it into that form than to try to plug it into that form. So depends on what I'm doing with it. Okay. All right, let me show you another place it would be hidden. All right. What if you had y equals 1 over x cubed?
Polar up.
Polar up. So it's going to be x to the what?
Negative 30.
Now, here's what you can't do. I get this a lot. Okay, you can't just start coming down here. This is what? That's y. This is going to be what? The derivative. So don't just start telling me everything's equal to each other. I've got to know what's equal. We're rewriting y like this, and then we're taking the derivative of that thing. So what's my power going to be? Everybody see why it's -4, -3, -1? So you gotta be careful with negatives. And again, if you turn to the back, they're gonna have a -3 over x to the 4. And if I've got to start doing slopes or equations of tangent lines or anything like that, that form's better for me to start. Okay? So is everybody okay on the power rule? Do you understand what it is? So what would the derivative of this? You go find me this derivative real quick, man. Your function's y equals x. Now, I don't see a power. What's the power when you don't see it? 1. So my derivative, that 1 comes down. That expression stays the same about how it goes down. What's the power going to go down to?
0.
Well, what is anything to the 0 power except 0 to the 0? 1. So the derivative of x is just what?
1.
So it's not a special formula. Sometimes I'll write it down like it's a special formula, and you're welcome to, but it's really just a special case of this. But if you want to write down it separately, you can. All right, here's a third one that's going to be really helpful to you. What if you have a constant in front of your function? Now, if you have a constant in front of your function, what can you do when you had a constant with limits? What can you do with that constant? You can pull her out. That's going to work here too for the same reason. Okay. Now think about, again, I'm just going to kind of hand wave at it. You understand that you would have a c in front of x plus h, and then you'd have minus a c in front of your f of x, and all that would be over h. So all they would do is take that c and what? Factor it out. Is everybody with me? So I've got a c times that, and then use that limit rule which says if you have a constant times a function, you can take that constant and what? Pull it out front, and that is the definition of the derivative of f of x. So that's why you've got permission to take that constant and just pull it out front. So I need to understand, here's what you're really doing. If I gave you this. Y equals 2x to the 5th, instead of just x to the 5th. And I want the derivative. Do you see that that's 2 times a function? So what I'm really doing is taking the 2 and pulling it out, and then I'm taking the derivative of the x to the 5th. Now, we've already said, what's the derivative of x to the 5th? 5x to the 4th. So what do I end up getting? 10x to the 4th, thank you. So it looks like, it ends up being what you end up doing, what you understand why you're doing it. When you bring that 5 down, if there's a number already there, what do you end up having to do with them? Multiply. Okay? So it comes out to be a very handy theorem that we need. Okay. All right, let's look at this one. Suppose you have more than one. Suppose you've got one function added to another function. Okay. Now, when you had the limit of a sum, could you separate them?
Yes.
You could, couldn't you? You can do the same thing here. That's going to be the derivative of the first one plus the derivative of the second one. Now, think about why that would be true. So your f of x plus h minus your f of x. So it's your original here. Is everybody with me? And then here is your original with your x replaced with what? X plus h. So you understand, if I wanted to prove that, if somebody said prove, this is what somebody did, prove that works. They've got an f of x plus h plus a g of x plus h. That would be their f of x plus h. And then minus. And then their original would be f of x plus g of x. And all that would be over what? Over h. Now, that first bracket doesn't do me any good, so I can just drop it off. But I've got to distribute this, so it's going to be a minus f of x and a what? Minus g of x. Now, I'm going to rearrange some things, but if I were doing a proof, I'd have to do something else. You can't just rearrange things when you've got addition and subtraction, because you don't have a commutative property of subtraction. But what can those subtractions be turned into? Addition of a what? Of a negative. So if I just change them to the addition of a negative, now I can start moving stuff around. And I want to regroup it. I want to group this one with that one. And then I want to group that one with that one. And my reason would be commutative property of addition tells me I can do that. Then I'm going to go back, instead of having plus a negative, what can I turn that back into? What's the same thing as adding an opposite? Subtracting. Then I'm going to take one fraction and break it up into the sum of two fractions. That would be f of x plus h minus f of x over h plus g of x plus h minus g of x over h. Because when you add fractions with the same denominator, you keep the same denominator. But don't you have a limit rule that says the limit of the sum is the limit of this one plus the limit of that one? So the limit of this is just the derivative of f of x, plus the limit of that one's just the derivative of what? G of x. Somebody fix that. So that's a proof of why that theorem works. So if you want to do an example, all it's saying is, suppose this was your function, x cubed minus 4, or plus 4. And I told you to find the derivative. Well, I've got permission by this to do the derivative of this one plus, and then do the derivative of that one separately. It gave me permission up here. It told me to add my functions and then take the derivative. And down here, I take the derivative first and add second. So I've got permission to change the order of what I'm doing. So what's the derivative of x cubed? 3x squared plus, what's the derivative of a constant? 0. So my final derivative is just what? 3x squared. Are we okay? Now, it also works if there's a minus. So if they were separated by a minus, I'd still be in good shape. Now, might have time, we'll see. What I'm probably going to do is do the proofs next time. Now, you figured out by now, do I like trig? Yes. I love me some trig. So I'm telling you, you better learn these trig derivatives because they're going to be on every test. Are we good? We're going to start off with 2 and build our way up. All right? But you need to learn them because they're all through Cal 1, Cal 2, Cal 3, Cal 4, and forward. All right? You can do it. You can do it. All right. You can just flat out memorize them. I'll show you why they work another day. I've got time, but they're in your book, I'm pretty sure in your book, they're pretty good to follow. Okay? The derivative of sine of an angle is sine of x is cosine of x. And the derivative of cosine of x is negative sine of x. So you've got to memorize which one does the sine stay the same and which one does the sine switch on. Now, kind of preview of coming attraction. What they're trying to do in the book right now is just give you the basic angle, just x. Later, it's going to be like the sine of 6x, or the sine of e to the x, or the sine of the tangent. Everybody with me? They get more complicated. All they're trying to do right now is get you to learn the words. So the derivative of the sine of 5x isn't going to be exactly the sine of 5x. That's going to be part of it with something else. But all we're trying to do right now is get you memorized. The derivative of sine of an angle is what? Sine of x is what? Cosine of x. For me, it was the same. The derivative of cosine was what? Negative sine was counter. So that's the way you should remember it. So I don't care how you remember it, but you don't want to get the negative in the wrong place. Now, what I'm going to do for a minute is I'm going to give you some to work. All right, for practice. And then we can't move, okay? But I am going to let you kind of turn around and compare your answers. Everybody with me? All right. So look in your books on page 139. Okay. Why don't you try number 12, 14, 20. Ooh, I like 22. So you work those forward for a minute.